it to my computer. Okay, and I'd like to start sharing the presentation. So welcome to the MUSICA tutorial series for introducing you to MusicBox. MUSICA is a multi-scale infrastructure for chemistry and aerosols. I want to begin by introducing myself. I'm Mary Barth. I'm a senior scientist at NCAR in the atmospheric chemistry laboratory, and actually also in the mesoscale microscale meteorology laboratory. Matt Dawson and Yang Li are also will be presenting and demonstrating MusicBox to you today. Matt is a software engineer at NCAR in ACOM, and Yang Li is an assistant professor at Baylor University. So we're going to begin today by myself giving you a quick introduction and overview of MusicA, and then Matt talking to you about how MusicBox works, and Yang will follow that with a demonstration, and then we'll spend a bunch of time doing a hands-on exercise. And then we'll wrap up by introducing you to the command line version of MusicBox and go from there. So looking forward to working with you on this. And to begin, I wanted to acknowledge the MusicBox developers and testers. And so Matt Dawson's our lead software engineer working on MusicA and the MusicBox efforts. But prior, before Matt even showed up, we were working on MusicBox, and Andrew Conley was leading that. And so really need to acknowledge his beginning leadership there. And I want to also note that we've really have done a lot of development using student assistants. Simon Thomas really got the MusicBox interface part developed, and Joanna Olson last summer did a lot of evaluation and testing. And so we're planning to have new students assistant startup, and this is like the first time I'm going to tell you this is a collaborative thing. And if you would like to contribute to MusicBox development, please let us know. So MusicA is a new model independent framework, which will enable chemistry and aerosols to be simulated at different resolutions in a coherent fashion. And so we envision this infrastructure to look like the schematic here. So there's a section here that we have as a chemistry and aerosol suite that we see hooking into a standardized interface that will, we hope, allow us to work with any atmosphere model. And so that will provide the ability to work with a variety of chemistry and physics schemes with these different atmosphere models. And in some cases, we can couple this to an Earth system set of component models. It'll work in the whole atmosphere framework, going from the troposphere to the thermosphere. And for those of you who have heard of SEMA, the System for Integrated Modeling in the Atmosphere, MusicA project is part of SEMA. So for those of you who don't know a lot about MusicA, we do have a web page, and we have a vision paper about MusicA in bands. So MusicBox is really just a box model version of MusicA. So you can take that same schematic and really cut out the Earth system component models and think of the schematic this way, where the atmosphere model is where we're prescribing environmental conditions, we're prescribing photolysis rates, prescribing emissions or depositions as a chemical reaction. So that can help us enhance our research by conducting simulations focused on the chemistry and provide a tool for teaching atmospheric chemistry in the classroom. And so one reason we're having Yang Li demonstrate MusicBox to you is because she made use of it this past fall in her classroom teaching. So we asked you about what potential applications that you were thinking MusicBox could be used for. And we gave you a variety of choices, and this is how things broke down. So, it seems like there's a lot of equal interest among different types of efforts, including chemical mechanism development, doing studies of PBL or plume chemistry. And then many of us want to work with our output from the 3D models or with observations. So it's really nice to see that that spread in interest. We also asked you if you've used a box model before, and it turns out about half of you have not, and half of us have. And of the existing box models, the Chapman Chemistry model is one, and the foam model were two of the more popular ones that were used. And then many of us had our own versions or other types of box models. And so we wanted, from those of you who've worked with other box models, we wanted to find out what you like about them and what you don't like about them and what features you would want to add to the box modeling. And that's, we were asking those things motivated because we want to figure out, what ways to improve MusicBox as we continue to develop it. And so you can see the list of things that people said. Ease of use was definitely a big plus for box models. Having it free to download. Some software is not free to download. So just to give you a heads up, MusicBox is free. It runs on a browser interface, and it also runs via command line in a terminal window. In the interface method, we have plotting capabilities, and we're trying to make this as flexible as possible. Again, going back to our MUSICA infrastructure goals. And then, of course, it's important to have documentation. And then we asked about what things are difficult. And I think maybe the number one thing is this top line. It's always been challenging to configure files for input to these box models. And I've used the BoxMox model myself, and that can definitely be a challenge. I've been there. Some people mentioned issues with operating system compatibility or needing different compilation options for different environments. Some others mentioned not always easy to make changes. And then, to me, the other one was, this bottom line, you had to revise the source code to change the chemical mechanism. And so with MusicBox, we are trying to provide multiple ways to provide input. It may not all be in there too, but we have the pathway forward of providing input in various ways. One thing that we added was the ability to download configuration files that you can then have in your home directory, and you can upload again for the next time. MusicBox uses Docker, and so that will address a lot of the operating system compatibility. And then the new features. So what things don't exist right now that you would like to see, and so this ability to test different chemical mechanisms or changing your chemical mechanism is a popular feature to have. Having direct calculations of photolysis rates, and having the ability to do dynamic input data. Another important one that we need to move to is having aerosol chemistry and gas to particle partitioning, and the ability to things like constraining a species, which some box models do offer that feature. So again, in MusicBox, just to remind you that it is under development, and we are planning to connect MusicBox to the NCAR photolysis tool, which is actually being refactored at the moment. We are also having our short-term plans to add the heterogeneous and cloud and aerosol reactions. And you'll see that we do have ways in MusicBox interface to easily test chemical mechanism changes. And I wanted to point out one more thing that we've been working on, is that the analysis, the results that is continually being developed. And this is another place where the community can contribute. But one thing that our student assistant worked on last year was coming up with sort of a flow reaction diagram. And this is for the Chapman Chemistry mechanism, where the blue and green, or the blue balls are trace gases, and the arrows are showing reactions through these green balls. And you can see via this flow diagram, what are the important reactions? So the thicker lines are the one more dominant reactions, and the thinner lines are not as strong. So sort of an interesting way to visualize how the chemistry is behaving. So I want to end by talking about mentioning the MUSICA goals. You're going to hear me repeat over and over again that our full intention is to develop this collaboratively with the community. So if you're interested in contributing, it would be great. So this is not just for MusicBox, but also for MUSICA, for 3D modeling. We'd love to have you use the released model configurations. We'd love to have you analyze existing output. And for both of those, we have previous tutorials, and you can go to our tutorial webpage and see recordings of those tutorials. And then you can also contribute to the model development itself. You can do that by joining working groups, or like with my MusicBox, you can contact us directly, and I'll give you that information at the end. So I'm going to stop there and pass the baton over to Matt, who will give an overview of MusicBox.
Right. Hi, everybody. Before I start on the design of MusicBox, I'm going to copy and paste the link to Docker Desktop into the chat. If you'd like to follow along with the hands-on portion of the tutorial and you haven't yet had a chance to install Docker Desktop, I would suggest you do it now. It's pretty easy, but it does require that you restart your computer. So if you start downloading it now, you should be back in time for the demo. Right, so the design of MusicBox. MusicBox is split into two quasi-independent components. There's the front end that we've been calling MusicBox Interactive. This runs in a web browser and allows you to configure chemical mechanisms, set up conditions, run simulations, and analyze results. And the back end of MusicBox is a command line application written in Fortran that does the actual chemistry solving. So when you run interactive, you don't really see the back end of MusicBox, but it is running. So if we go to the next slide, I'd like to talk just a little bit about interactive. You'll see a lot of the features in the demo, but I'd just like to talk a little bit about what's happening on the back end. So if you've had a chance to look at the MusicBox GitHub repo, you should see on the README page that there's really two steps to getting up and running with MusicBox. The first is to get Docker Desktop installed and running. And the second is to copy this command, this Docker run command you see here in purple, into a terminal window. And so I'd like to talk a little bit about what happens when you do that. So the first thing that happens is Docker looks to see if you have a local copy of the MusicBox image. So if you've run MusicBox before, you likely have this and it'll use it. If you don't have it, it'll look on Docker Hub and download it. And this can take about a minute or so, maybe a little bit longer, depending on your internet connection. But once it's downloaded, you can use it repeatedly. So every time you start MusicBox up again, it should be much faster. So after it gets the image, it starts up a container on your machine based on that image. Inside the container is essentially the operating system, some support libraries, and then the MusicBox applications. It opens a port. If you see the -p section of this command, it opens a map between a port in the container, port 8000, and port 8000 on your local machine. And this is what allows your browser to communicate with the web server that's running inside the container. So after all that's up and running, you can go to a browser, open up localhost 8000, and start using MusicBox. And what happens is that inside the container, the web server is handling requests from the browser based on your input and setting up some configuration files for MusicBox. And then when you indicate you want to run the model, it runs inside the container the command line version of MusicBox. using the configuration files that it's been building for you. And then afterwards, it allows you to request plots of the output or to download the output directly. So one other important thing, and Mary already mentioned this about MusicBox Interactive, is that it's primarily a student-developed project. Simon Thomas, who worked with us for about a year, wrote most of the code for Interactive. We have 2 more students, like Mary mentioned, coming in the summer. One of the things they'll be working on is to adapt Interactive to be a multi-user service. This will allow us to host MusicBox, and so people will be able to go to the MusicBox webpage and run simulations directly within reason, of course, instead of having to run it locally in a Docker container. So we think that'll make it hopefully even more useful, more broadly useful. And we really think it's a great project for students because it's the front end is written entirely in languages that people learn in school and use regularly. And it allows for a lot of creativity too, especially with like the graph network plots that Mary was talking about. We think that students have enjoyed working on things like this. So that's the front end. If we go to the next slide, I'll talk a little bit about the command line version of MusicBox, which is the back end. And to do that, first I'd like to mention what we see as the role of MusicBox in the overall MUSICA project. So we really see it playing 3 roles. The first is, of course, we'd like it to be really functional, easy to use box model that people can use for comparisons with observations and experimental data, as well as in education. We also see it being useful as a test bed for new science contributions to the MUSICA project. We envision new science modules first being introduced into MusicBox, where they can be tested under sets of standard conditions before then being made available for 3D MUSICA simulations. The third role we see for MusicBox is sort of a test bed, or maybe more of a demonstration platform for some of the standards we're trying to introduce for software contributions to the MUSICA project. We've been discussing between the scientists and software engineers involved in MUSICA over some time about the need, in order for MUSICA to be a stable, sustainable product over many years, even as new science features are continually added. It's really necessary to come up with standards for the software contributions coming in. And so I'd like to talk about 3 of the things that we've been discussing that are based on sort of contemporary approaches to handling complex software packages and how they relate specifically to MusicBox. So if we go to the next slide, the first thing is that we would like to have science components that are introduced to MusicBox and hopefully MUSICA in general, build as standalone software libraries with well-defined application programming interfaces or APIs. And so this cartoon on the upper left, this is sort of shows how libraries interact within MusicBox. So the MusicBox application is shown in the box in the upper left. It makes use of a library that we've been calling MUSICA Core, which is shown on the lower left. This is essentially just a collection of utility functions and types to provide functionality that's often present in higher level languages, but is not present in Fortran, which is the language that MusicBox is for the most part written in. Things like string types and lightweight wrappers for JSON readers and writers, things like this that can be of general use to the different components of MusicBox. In addition to MUSICA Core, the individual science components of MusicBox also build as standalone libraries. And currently there are 2. There's the MICM chemistry solver and the CAMP chemistry solver for multi-phase chemistry. And we hope to be adding more, as Mary mentioned, the photolysis package, aerosol package such as NAM aerosols moving forward. The way MusicBox is set up is that all the science components are expected to extend an abstract component class. This is defined sort of a general way that MusicBox interacts with all science components. I'd like to talk a little bit about how that applies slightly differently to a software package like MICM, which is being developed as part of the MUSICA project, and something like CAMP, which was developed externally and is maintained externally to MUSICA. So for MICM, because it's part of the MUSICA project, it natively contains an extending class of this abstract component class. So in order for it to be used in MusicBox, all you have to do is link the library and indicate to MusicBox that you would like to make them available. Whereas something like CAMP is, it's developed externally, so obviously it doesn't have an extending class of component in its software library. So in that case, we introduce a lightweight wrapper in the MusicBox source code, shown here in the upper left. You'll see in the source components a camp.f90 that is an extending class of the component class that wraps the CAMP functionality, so that MusicBox can then interact with CAMP the same way that it interacts with other science modules like MICA. So we think that this structure can go a long way to, sort of setting up the modular system that Mary was describing that is a goal for MUSICA. So if we could go to the next slide, talk a little bit about testing. Standards for test coverage are very commonly applied, especially to complex projects. We would like to introduce a goal of having at least 80% coverage by unit test for all science contributions. We think that this will go a long way to maintain the this complex code base stably over many years, hopefully. We will be encouraging contributors to obviously build their library or build their software as standalone libraries, but then apply a lot of continuous integration in order to automate the testing, which makes it much easier and then requires less work by developers to keep running tests, for example. So if you look at, for example, the MUSICA core library, we use GitHub Actions there so that whenever someone pushes new code to the repo, the GitHub action will run the tests in a Docker container. It will also generate the code coverage report, which it sends to codecov.io, which assembles it into a nice, easy to interpret set of graphics. So you'll see in the MUSICA core README, there's a badge that indicates the overall test coverage, which if you click on it, you can then go see the individual test coverage of specific files and even down to individual lines of source code. You'll see that right now we're at 54%. We're not at our 80%, but our goal is to get there, and we're pretty confident we can do that. So if we go to the next slide, the last thing I'll just mention quickly is that another goal that we have is that science components be runtime configurable. This is what makes something like MusicBox Interactive possible, because at no point do you have to modify source code or recompile the model. But what this means is moving a lot of hard-coded configuration parameters out of the source code and out of the build time configuration and moving it into runtime interpreted configuration data. And so we think that this is very common in the software that we all interact with on a daily basis, and it goes a long way to improving the user experience. So I think that this is something that's important for science software as well. And so I think that's it for a quick tour of MusicBox design. And now Ying is going to do a demonstration of MusicBox Interactive.
Yeah. Okay, so we have the demonstration, and next is the hands-on exercise. So I have a document that I put up on our tutorial webpage. So that link is here. Let me get that into the chat real quick. I can move things. There we go. The link address and find the chat. So that hopefully will get you to the document. And so I will also put this up on the screen. Let's see if I can do new share here. Actually, Zoom. There we go. Let's see. Okay, so can you see the hands-on document on the Zoom meeting as well? Young, maybe, can you see it? Yes. Victoria.
Yes, I can see it. Yep. Mhm.
Great. So I just want to go through it quickly, but with the goal of you working on your own. But the idea is shown here that you're going to start MusicBox and open up MusicBox interface, and then do what Yang was just showing you with really just the Chapman Chemistry example. We want to keep it simple for during the tutorial, just to get you to practice working with all the different buttons that Yang was working through. So start with that example. You'll review the chemical species and the reactions. Just check to see, you can see what was shown in the demonstration. You can then review the conditions for running it. Again, looking at the initial conditions. One thing you'll notice is that our examples are using SI units, but if you have something that, concentration that in molecules per cubic centimeter, so it's you can input that in and change the units of that particular species. If you know something in molar mixing ratio, then you need to know the density and to do the conversion. And so there's a unit conversion calculator available to help make those calculations. And then again, checking the evolving conditions section as well. So like Yang was showing, I want you to run the model. I want you to plot the results. So just keep trying different things, try different units when you plot the results and see how things come out. Test the downloading the configuration file and the result files. Go to your downloads directory and unzip those files and see what's contained in the configuration and download results. The main items files are CSV files, and so those can easily be then imported into Excel or read by any other analysis software. And then go back to the MusicBox interface and start changing things. Try it with different temperatures and pressures. Try it with different initial concentrations, and change the example. So when you download that configuration file up above, you will have a CSV file available, and you can go in there and make some changes, maybe double the photolysis reaction, whatever you want to do, and then upload the file. So go practice that and run the model and plot the results. And then the last thing that we'll have you do is add some chemical reactions. And so that we just could have you add some Hawks chemistry to the Chapman chemistry mechanism. So you'll do that by adding OH and HO2, and then adding the reactions for OH and HO2. So I provided the information of the reactions up here. And you can add initial concentrations, but many of you know that OH and HO2 are very fast species chemically, so it's not really necessary. Then you can run the model and plot the results. You'll notice when you plot the results that the answers are a little bit different, which is kind of cool. And then if you download that configuration file, you now have your new created mechanism, and you can use that to load the configuration file the next time, just like Yang was showing you in the demonstration. And so on the last page here, I show a few of the results from doing these hands-on exercises. So you can kind of check how that compares. I also want to mention that there is a full stratosphere chemistry mechanism available. It's not as an example, but it is available. And going back to the beginning starting page for MusicBox, you'll see in the first paragraph, visit this repository, and you can go into the stratospheric mechanisms folder and the full Chapman folder and get the configuration files from there. Okay, so we have that. I think one of the other things we wanted to mention for those of you who have worked with MusicBox before, it might be good to refresh things. And I don't know if Matt is back into the main room or not, but there are a couple of commands to do to refresh MusicBox. And let me see if I can pull that up myself. There it is. So I'll put these commands into the chat for those of you who have already merged MusicBox. Actually, I have a chat there. There it is. Go. Yeah, so that's kind of cleaning up your MusicBox image in the Docker system, and so you'll be reinitializing MusicBox there. And have Matt tell you about the command line version. So you've gotten used to what the MusicBox interface is like. And so just to let you know, MusicBox interface, as you're finding out, is really nice for testing things, playing around with the chemical species and mechanisms of different conditions. But you may not want to do all this manually for every simulation you want to do. And so the command line version is really useful if you do have lots of simulations we want to do. So Matt, do you want to go ahead and tell folks about the command line version?
Sure. Would you mind if I share my screen instead so I can flip back and forth with the...
I don't mind at
terminal?
all.
Cool, thanks. And let's see, share screen. I'll just share the desktop, it'll be easier. Okay, so yeah, as Mary said, anyone can use the command line version of MusicBox directly. It's useful for use in scripts and other things, running large numbers of simulations, and it works with the files that you generate in interactive. So hopefully it's easy to modify things in interactive, save the file, and use it at the command line. So I'm going to walk through that process quickly here. So I have MusicBox running. If we go to the Chapman example, select it, and then run the model, you'll see the last option on the left menu is download, and you can download results or the download configuration file. So if you click on download configuration file, you will get a file called config.zip, which I've already downloaded, so I'll just use that one. And actually, let me go back to these instructions so we can follow them together. So then in a browser, and this is the browser where I was running the web server, so I'm going to stop it. And oops. All right, so the first step is to create a file that can, or a folder that can be shared between your local machine and the container. So I'm going to do that now. And then we need to copy that configuration file that we downloaded from interactive into that folder. So for me, it's in my downloads folder, and it's called config.zip. And I'm going to copy it into this folder that I just created. And then I'm going to cd into that folder and uncompress the files. And you'll be able to see that there's now a folder called config. And inside config is a CSV file with some evolving conditions. There's the myconfig.json, which is the main configuration file for MusicBox. And then in the camp data are the mechanism description files that are needed by camp, which is the backend chemistry solver. So I'm not going to change anything. I'm just going to leave those there. And then I'm going to copy and paste this command, this last one. I'm not going to type this in, but then we can talk about what this does. So there's several ways to work with containers, and we can talk about what the options are. This was nice just because it is a single line and will run the model. So let's copy paste it in. You can see this is the output from the command line version of MusicBox. You can see the variables that get registered by the various science modules within MusicBox, which modules are accessing those and which ones have requested the ability to modify those properties. And then you'll see the progress of the simulation as it runs. Chapman Chemistry is very fast, so it goes pretty quickly. And then you'll see in the config folder, you'll now have an output.csv file, which is the output from the simulation. So I'll just say a little bit about what happens when you run this Docker run command. You'll see that it is different from the one that starts the web server in a few ways. One is that you don't do the port mapping, so you don't need any ports open between your container and your local machine. It mounts this folder that you created inside the container. And so that sort of acts as the exchange, sort of the way to exchange data in and out of the container. So there is a MB files folder inside the container as well as on your local machine, and they point to the same place in your file system. And then you'll see again the ncar/musicbox image listed, and after that, bash-c runs bash commands in the container directly. So it changes directory into the MB files folder that you created and into the config subfolder of MB files that was created when you unzipped the MusicBox files. And then it runs the MusicBox command line version, which is in the build directory, and it's called music_box. And then it gives it the myconfig.json file, which is the primary configuration file for MusicBox. It runs and closes the container immediately, and then you have the output. And there are other ways to work with the container. If anyone's interested, we can talk more. There are ways to, sort of go through the looking glass into the container, run the model in there, and then exit and copy things in and out. So there are several options. So this is just one of them. And I think that should be it. Are there any questions about this?
Yeah, and Matt, you can keep sharing your presentation. Just go to the last slide.
All
right. Yeah, that next one. Yeah, so that completes our MusicBox tutorial. And so as Matt asked us, we all ask, if you do have any questions or you have suggestions for MusicBox, feel free to contact the MusicBox team. If you would like to contribute to MusicBox, please also contact us. So we have an email address, MusicBox support, that you can use to ask questions, offer help, whatever it might be. And actually, I think no one showed that, but at the bottom of the MusicBox interface, there's a couple of links, so things like report a bug. Yeah, you're welcome to go there. Right, how to use, and goes back to the beginning, but report a bug will take you to writing an email to bring up issues with MusicBox. And then if you go back to the presentation, Matt, so once again, I want to thank all the developers and testers that have worked on MusicBox, and I really appreciate all of you two participants who have come and joined us and spent a couple of hours working on it. And we look forward to getting feedback and hearing from you. So if anyone has any questions, this is a great time to ask. And if not, feel free to leave the meeting. It's been really a good time. Thank you.